Okay.
And so these are kind of why we care in a PDE seminar about functional analysis, about this infinite dimensional vector space idea, is because now we can treat sets of functions as a vector space and use all of that language, all of those tools in discussing PDEs and discussing differential equations. So then we have more structure, like I was saying. We can define a normed space. So a norm is just a vector space V. So I'll just say, yeah, it's a vector space V with an operation which is a map from the vector space to be general to the field of scalars, but complex or real numbers are usually all we care about.
I don't think it's always to the reals, and the norm, even if it's not complex, it must be real, but it cannot be complex number.
Right. I'm thinking of something else. And it satisfies, so then for all scalars alpha from our field, and for all vectors from our vector space. This is, again, the length, the norm that we've been dealing with in, well, the general abstract axioms of a norm that we've touched on in all of the coursework that we've had. We need this structure in this infinite dimensional sense because it helps us sort of talk about different spaces. You know, for the same reason that we define normed spaces on finite dimensional vector spaces, this definition is useful. So we satisfy, we'll just say the complex numbers just to be this is.
When you wanted to take absolute value and then you decided not to, the absolute value. So how do we call that?
Right, that is the triangle inequality.
Right.
And I'm missing, oh, right.
What else? Right.
Okay. So this one is very important, is very useful. It's the triangle inequality. And it comes from, again, in R2, if we have a vector, then the length of this vector, any triangle, the length of this vector is always greater than, well, it's always equal to the sum of the length. I'm sorry, it's always, the lengths of these two vectors is always greater than the length of their sum. And that's the geometric picture of why this is called the triangle inequality. We force it, or we assume that it's true in a general vector space. And again, this definition of norm allows us to discuss very useful things like defining normed spaces. So an example of a normed space.
Why don't you define norm in those two spaces that you define on S?
I'm not sure we can define a norm on S. Can we?
Well, it will be called differently, but on a space of sequences.
Right, yeah. So that's what I was going to do. Yeah. So we can define sort of a subspace of S. We can call it L1. And this will be the space of all vectors X from this space S, such that the sum of the components, I'll use the same notation of X's, components of this vector.
The absolute values.
Such that the sum of the components is a finite number. And then the norm on this space, or a natural norm, is that if we have a vector from this space, we can say that its norm is the sum of the absolute value of the components. And we can be more general, and we can define LP spaces where we take pth powers, and then in the definition of the norm, a pth root. For functions, again, we have to do the same thing. So we can define a function space, say L2, and this is usually defined over a set. So this is maybe Rn, or it could be so.
0, 1, I mean, it's
sure.
Is an example.
And this would be all of the functions from our previous set. That's not true. This would just all functions from 0, 1 to R, such that, this notation, such that the integral
from 0 to 1.
Right.
Mm-hmm.
And again, we can be more general. We can choose a different space here. We can change this 2 from being a 2 to being any real number greater than 0, although less than 1, only topologists.
So what's the norm in
So the norm here is if we have a function that is an L2 function, we say that its norm is this integral. To the 1/2.
Right. So
And then we can show that this satisfies all of these axioms.
So you could replace 2 by P and then you get LP norm.
Right. So are there any questions? Is this mostly review for everyone? Okay. And then I do want to note that almost always this space is defined using the Lebesgue integral. So we talk about a measurable space and measurable functions. But I think for this discussion, that will be a subtlety. He does go into defining all of these things on manifolds, where that, I don't know, may not be as much of a subtlety. Let me see. Is there anything else? Oh, right. So we immediately get from...
Well, let me give you an example, which is called Sobolev space, HS. Just write HS on the interval 0, 1. So these are all functions well, like that, right, from 0, 1 to R.
Sure.
Right, whose S derivative is in L2. Which means that you can write it like the S derivative square integral is finite, basically. The L2 norm of S derivative is finite. Yeah, that's basically. So you can write that integral, where instead of squaring f, you square its S derivative, which means that the derivative has to be nice, has to be integral. So these are kind of controls the regularity or the smoothness of the function. These are really important in PDEs.
Right. And then for generality, you can also define a P rather than just using 2. But the reason we use 2 is the notion of an inner product is only in L2. So I think the first kind of Sobolev space is seen more often. Oh, right. And then this notion of norm, immediately, again, we've talked about metric spaces here, places where we can define a distance between two sets of, between two objects in a set. This notion of norm immediately gives us a distance. So if we take two vectors, v1 and v2, from a normed vector space, we can just say that the distance between these is the norm of the difference between them. So every norm induces a metric, and therefore we can treat every normed space as a metric space. The important bit in functional analysis, or many of the things that are discussed, is this metric space. When we view this normed space as a metric space, we require it to be complete. So first we'll discuss what that means a little bit. So we take, say, a general metric space X. Or a sequence is Cauchy. Yeah. So a sequence of elements Xn is Cauchy when the distance between, it's in a few
If
years.
for any epsilon greater than 0, there exists a k greater than 0, an integer actually, integer k, right, such that for any n and m greater than k, and then write what you want to write. The distance between xn and xn is less than epsilon.
Right.
So what does it mean geometrically? That
So
the elements of a sequence get close to each other, right?
they approach some limit. You know, every Cauchy sequence.
Well, you don't know yet whether it approaches some limit, but basically
right,
they get close to each other. They accumulate.
Right. And so every convergent sequence is also a Cauchy sequence.
Well, you have to define what the convergent sequence first is.
Sure. So, has anyone not had analysis? Should we just write that down?
Well, I guess that's enough to have just Cauchy sequence, and then you can define convergence.
So the reason we care now about convergence, about this metric space definition, is we want to bring some of the analysis language, some of the things that we do there, into these infinite dimensional spaces, because again, the motivation is to discuss functions. The motivation is to take a lot of this theory and be able to discuss functions so that we can discuss differential equations. So we can define a metric space. Did I write this? Yeah, okay. So we can now say that a metric space is complete if every Cauchy sequence converges or has a limit in the metric space.
Right.
So that means, you know, a simple example that's usually given is the sequence 1 over n. We could define this sequence for n, you know, greater than n is an integer, a positive integer. So the sequence on this interval does something where each successive element gets closer. If the interval we're talking about, if the metric space we're talking about is the open interval from, say, 0 to 1, or the half-open interval, then this Cauchy sequence doesn't converge. So this would not be a complete metric space.
It converges to something that is not in this set.
Right. Whereas if we include this point at 0, then what this Cauchy sequence converges to is in the space that we're talking about. So it would be considered a complete.
Give an example of continuous functions whose sequence of continuous functions whose limit is not continuous.